Hey, welcome back to Math 7195. We're now in Unit 3, Video 2. We're talking about discrete probability distributions, and in this video we'll be talking about specific ones. We'll be continuing to discuss the binomial distribution a bit, and then we'll move on to a few others, the Poisson distribution, hypergeometric distribution, geometric distribution, and the multinomial probability distribution. So we can dive right back into our lecture notes. We're currently on page, looks like 11 of our notes. And we were talking about the binomial distribution. And we saw that the formula for calculating binomial probabilities was a little bit tedious to work with. It has some, factorials and exponents and such in it. It turns out that there are some tables built that will assist us in these calculations. So let's do an example using something called the cumulative binomial table. So we can start out with an example, and then we'll see how it goes from there. Changing our example, we now have 70% of all Masons call in sick at least one day in December. Find the probability that at least 7 will call in sick in December if 10 are randomly selected. So first thing we have to do is take a look at this and make sure it is a binomial situation. They either call in sick or they don't. So at least we know that there are only two possibilities. We have a fixed number of trials. We're going to look at a group of 10. And we're looking for, I guess now we have to check to make sure that our probability is fixed. And it looks like it is. They're just saying 70% of the time, and it doesn't change. And we'll assume that they're independent of one another as long as the 10 people we're choosing aren't influencing each other in any way. If these are 10 people that all work at the same place, that might not be true, because if Bill decides he wants to go fishing, he might, convince his buddy Steve to, call in sick so that they can both go fishing together. And then we would violate the condition that, each element in there is independent of every other one. But assuming that these were just randomly picked and they don't know each other, then I think it's safe to say there's no relationship. We want the probability then that at least 7 out of 10 call in sick. So that means 7 or more. Representing that as a greater than or equal to then. We learned that sometimes it's easier to work with the complement. In this case, if we were solving it directly, it wouldn't be. We would just calculate 7, 8, 9, and 10. We'd have to calculate 4 probabilities and then add them all up. But I'm going to convert it to its complement, and we'll see why in a second. The opposite of greater than or equal to 7 is less than 7, and because it's discrete, being less than 7 means that you're 6 or less. Now, the reason I converted it to a less than or equal to question is that even though it would be more work to calculate by hand this way, this is the way the cumulative binomial table works. It helps you solve problems that are in the form less than or equal to. To solve the probability of less than or equal to 6, we go to this cumulative binomial table given below. We'll see that for this table, our n is 10. And we're looking for x less than or equal to 6. That puts us in this row of the table. And then across the top are the probabilities of successes. We want 0.7. So we're in this column, and we get this probability here. So the table solves this piece of it. And we're done. No real calculation required, except we have to do 1 minus this answer. So 1 minus 3504 is 0.6496. Now, tables were really important before computers, I suppose, but now that we have computers, we should probably take advantage of them. Excel has a binomial function built right in. It's called binomdist. It will help us solve individual binomial probabilities, and it will also do these cumulative probabilities. In fact, that's how I built this table. In your formula packet, you will be given a set of tables. You'll have a bell curve table, you'll have a t-table, you'll also have a binomial table. The one that we just used was right here. Basically, there's a different table for each n. So first thing you do is figure out your sample size, and then after you figure out your sample size, it will tell you which part of the table to be in, and then you can figure out your probabilities from there. So it's fast to use a table. In fact, I think I'm faster at using the table than using software, but I think we should learn how to use the software too. So I opened up Excel, and you can see here this question. I set up a table here where I said in our problem n was equal to 10, our probability of success is 0.7. And then I built a table here where I know my x values can go from 0 up to 10. And then I calculated the probabilities of each of those events. So in this first cell here, it's binom.dist. That gets us our binomial probability distribution. And the parameters are, the first value is your x. In this case, I want the probability of 0 successes in 10 tries. The next parameter is your n. In this case, it's 10. I just listed the cell reference there. The number 10 is in cell B1. I put dollar signs around it so that Excel knows to always look at that one spot when I copied the cell down. The probability of success is the next input. It's, in this case, 0.7. I could have hard-coded those numbers in. I could have said A5, comma 10, comma 0.7. And then at the end, it asks us for one more parameter there. And it's basically true or false. And it's asking us, do you want this to be cumulative or not? And in this case, I didn't want it to be cumulative. I wanted to get the probability of 0 successes in 10 trials. I didn't want less than or equal to 0. I wanted exactly 0. In fact, I wanted that for all of them. Once I calculated each of these probabilities, I just took that formula and copied it down. I plotted this so we could see the distribution. We can see it's skewed a little bit to the left. We can also see that for this problem, we were trying to get the probability of 7 or more. There, now that I have my cursor working better, I can point. We can see that these probabilities correspond to the areas of each of these rectangles. We want the probability of 7 or more. So we want this rectangle plus this rectangle plus this one plus this one. But to accomplish that, we did 100% minus 6, 5, 4, 3, 2, 1, and 0. The formula for that is here. It's 1 minus binomdist. 6 is we wanted 6 or less. 10 is the number of trials. 0.7 is the probability of success. And in this case, I did put a 1 on the end of the formula because I wanted it to be cumulative. We'll see that a bunch. There are formulas in Excel that have that little flag on the end for a specific case and then the cumulative case. So I think we can go back to our lecture now. And we saw that we matched this value. The next question here is, what's the probability of exactly 7 people calling in sick out of 10, where they are, still have a 70% chance of calling in sick? This is an equal to problem. We could use the formula. We could use the table. We could use Excel. If we were using the table, we would say it's x less than or equal to 7 minus the probability of being less than or equal to 6. If you do 7 or less and then take away the probability of 6 or less, that's the probability of exactly 7. Basically, you're adding up a bunch of rectangles and then subtracting out the ones that you don't want. So back to our, if we're going to read this off the table, I already have it circled there. It's 7 or less, which is 6172, minus 6 or less, which is 3504. So 6172 minus 3504. And we get 2666. So that's a way to use the table to get an exact value without having to use the formula. But it would have been pretty easy to use the formula. If you're a formula person, you'd say, okay, there were 10 things. 7 were good, 3 were not good. There's a 70% chance of being sick. I want 7 of those. There's a 30% chance of not being sick, and I need 3 of those. And you'll get the same answer. If you're an Excel person, I guess it would be binom.dist, and then we want 7 out of 10 with 70% chance of success. And in this case, we don't want it to be cumulative, so we put a 0 on the end of that function. So there's some, shortcuts for doing binomial problems. Binomial distribution is super nice in that when we learned about the expected value and standard deviation for just a general discrete distribution, the formulas were a bit ugly. We had to sort of build tables in order to achieve those things. Those formulas simplify greatly with the binomial distribution so that the mean ends up being just n times p. If 70% of your Masons call in sick and you have 10 of them, how many do you expect to call in sick? 7. 70% times 10, which is exactly what that formula is. The standard deviation is the square root of NPQ, where Q is just 1 minus P. Having the mean and standard deviation lets us talk about the empirical rule and Chebyshev's theorem again. So maybe we can make a decision using those things. There's kind of a neat feature of the binomial distribution in that, we saw that its shape changes. If little p, if the probability of success is small, then the thing tends to be skewed to the right. If the probability is large or high, then it tends to be skewed to the left. If the probability is somewhere in the middle, it tends to be fairly symmetric. And when it's symmetric, it starts to follow a bell curve. And if it's following a bell curve, then we get to use the empirical rule again. So we just need to find some rule to identify when is a binomial distribution shaped like a bell curve. And it turns out that the rule is if NP is greater than 5 and NQ is greater than 5, then we get a bell shape, or the normal shape. We need to satisfy both conditions. 5 is sort of a magical number. I'm guessing that we've plotted, thousands of these with varying N's and P's and found that 5 tended to be a pretty good fit to, be the cutoff between, when they looked like a bell curve and when they didn't. There's a quick example here that's supposed to convince you of this. I did an example where I just said, let's let N be 20 and P be 0.25. Then I typed, binom.dist. I guess they'll start with an equal sign. And then I put my x, which is this value, say it's in, A2. And then my n is 20, and my probability of success is 0.25. And I don't want it to be cumulative because I want it to list them all individually. So I figured out the probability of 0 successes out of 20, the probability of 13 successes out of 20, and all of 20 successes out of 20. And then I plotted all my results. Very bad graph, no titles, axes aren't labeled. Don't do this yourselves. But it gives me a chance to harp on that issue. When we look at this plot, it's pretty decent bell curve. Because it's a bell curve, then we could start, using our, ideas about the empirical rule where we said things like when you're within 2 standard deviations of the mean, you're kind of a typical or not unusual value. Does this meet the criteria? Let's check. NP is 20 times 0.25, which is 5. And NQ is 20 times 1 minus 0.25, which is then 15. The first one is greater than or equal to 5. The second one is greater than or equal to 5, so it checks out. In fact, this was one that was a really close call. Like we ended up equaling 5, and it still looks pretty good. So you can imagine that if we can get this number to be further from 5, I mean, this one would come down, obviously. We would get even more symmetry. But it still looks pretty good, even right on the border. Of course, I did do something kind of deceptive in this plot. In addition to giving you no titles and no labels and no legend, I also was deceptive, which is something I wanted to do here. My goal in this plot was to show you we have a bell curve, but you'll notice that I only plotted from 0 up to 12. I did not plot all the way up to 20 because I wanted to show you that it was symmetric. But if I kept plotting all the way out to 20, then it starts to look a little bit skewed. But not really. If you look at the values that I didn't include in the graph, to 3, almost 4 decimal places, they were 0 anyway. So I think I deceived, but not too badly. Had these been large numbers and I cut them off, then I definitely would have deceived. But not this time. But keep your eye open for these things. Even your teacher tries to trick you. Here's an example where we'll make a quick decision. We make solar panels, and it says that 10% of them need repair in the first year. We run the company and we have a 1-year warranty. And so we know how many of these things we had to go out and fix or replace. So maybe we're not satisfied with that 10%. So, we come up with a whole new design for these things. We spend lots of money changing the solar panels. We reconfigure the plant, and we hire new employees. And after a year, we'll know if we made any improvement or not. So, after modifying these things, after the design, then we wait a year and we see how many we had to fix in that year. After that year, we collected 200 to test. Assuming that the modifications had no effect, let's find the mean and standard deviation for the number of solar panels that would need repair in a group of 200. In this case, we have a study of 200, and we're assuming that we didn't improve these things at all. So we're saying that 10% are still defective. Is this a binomial situation? I think so. They either need repair or they don't. They have a fixed probability of success. And by success, I mean successfully breaking. We'll assume they're independent of one another so that we took samples from all different places so that, one that was sitting next to another one didn't influence another one, for example. So I think we have independence and fixed number of trials. So we have met the binomial criteria. So we can calculate our mean using the binomial mean, which is just n times p. So in this case, that's n is 200, p is 0.1, so we get 20 panels. On average, we'd expect 20 to be defective in a group of 200. We're going to calculate the standard deviation as well. Because it's a binomial, it's not bad. It's just the square root of npq. So in this case, the square root of 200 times 0.1 times 0.9. Q is just 1 minus p. Doing this calculation, we get 4.24 panels. I guess defective panels. These are the numbers that we would have expected before we made any modifications, because we don't know the defective rate yet. We haven't studied our 200 panels. We just, randomly selected them. We don't know if they broke or not yet. Now we checked those 200 panels and we find that 14 of them needed to be fixed or replaced. Is this unusual? Is 14 unusual relative to 20? Is basically what we're saying. It's smaller than 20. Great. Maybe we've made an improvement, but maybe not. Would it be weird to get a number like 14 if we didn't fix things at all? Let's first see if we have a bell curve. I mean, I've already plotted it here for you, and it does look pretty nice. Let's check the criteria. Remember, NP has to be greater than 5? Well, it's 20, so it's greater than or equal to 5. And NQ, that has to be 180, which is also greater than or equal to 5. So it checks out. We have a bell curve. When we have a bell curve, our criteria is if you have a z-score between -2 and +2, this is a pretty typical score. So let's calculate the z-score for the number 14. The number 14 is our x. We're studying our mean was 20, and our standard deviation was 4.24. This gives us a value of -1.41. So this isn't that unusual. It falls in the range. Now, if it's not unusual, can we conclude that it was worth the expense of changing the design? I like that 14 is smaller than 20, but it's not enough smaller than 20 for me to feel good that I've made improvement. I don't necessarily have significant enough improvement to make a conclusion. It is the first time I've said the word significant. Uh, had this z-score been -8, then I would say we've made significant improvement, likely. We still might not have, we might have gotten unlucky and picked a weird sample of 200 solar panels. We just picked the, you know, the best 200 in the group, and therefore we ended up with such a weird z-score. But I feel much better about making a conclusion if this had been -3 or -4 rather than -1. At this, with -1.41, I'm sitting here thinking maybe it helped, maybe it didn't. I need to study more. I either need to take a bigger sample from the year's data that I have, or I have to continue to collect data for some time to see if it made an improvement. Because this number of 14 could have been, is what I might have expected to happen even before I made any modifications. This is sort of an introduction to what we're doing in the course going forward, where we sort of evaluate things based off of a z-score. What is the probability of getting a result like this, assuming that nothing changed? If that probability is very low, then something weird happened and we think that we've made a change. If we get something that has a high probability of happening without the change, well, then maybe the change didn't really do much. So we're going to definitely discuss that more as we go along. But for now, it was just kind of a little advanced notice of what is to come. We've hit that binomial distribution pretty hard. There are other distributions out there. Another one is called the Poisson distribution. This one is similar to the binomial in some ways, and it's also different. We typically use the Poisson distribution when we're modeling queuing, and it often is the distribution that models arrivals. So it models like the people arriving at the bank to do banking. Or I put a bunch of other examples there. This distribution doesn't have a fixed number of trials like the binomial distribution did. It has a period of time. So we can model the number of people that arrive at the bank in the next hour. Sometimes 10 people arrive in an hour. Sometimes 3 people arrive in an hour. Each of those events has a probability associated with it. That probability can be calculated using this formula. It has 2 parameters, the number x and then the mean rate. Like it's the rate of arrival. We'll call it lambda. The formula is a little ugly. It's lambda to the x e to the minus lambda over x factorial. Excel has nice functions for it as well. Poisson dist and for an individual and Poisson dist for cumulative. In order to use this thing, when we had the binomial distribution, we always had to check, does it have 2 outcomes? Does it have a fixed number of trials? Does the probability always stay the same? Are the occurrences independent of one another? For the Poisson distribution, we also have to check those conditions. In fact, it's probably more important that we do this than the calculations themselves, checking to see that we can even use the model. Occurrences must be random. They must be independent of one another. So when I go to the bank, I don't influence you to go to the bank as well. And occurrences must be uniformly distributed within the interval used. So if I say arrivals at the bank in the next hour, people have to be just as likely to arrive in minute 1 as they do in minute, 53, which might not necessarily be true. If I'm talking about the bank, people are more likely to maybe show up close to the hour, because that's when they have, breaks in their schedule. I know when I'm planning my day, I'm more likely to go to the bank at 1 p.m. than I am to go to the bank at 1:22 p.m. So we can always fix that interval problem by just shortening it. What's the probability of somebody arriving in the next 10 minutes? And that way, during any 10-minute period, things might be, uniformly distributed. The mean for the Poisson distribution is just the rate. So if on average 8 people arrive per hour, well, then that's what lambda is, and that's what the mean is. The standard deviation is nice there. It's just the square root of lambda. I've already discussed the differences between Poisson and binomial. We can take a look at their graphs. The thing depends only on lambda, and it has no upper limit. The binomial always had that fixed n, but the Poisson distribution, 10 people can arrive at the bank during an hour, but maybe 1,000 people could, or 1,000,000 or 100 million. Sure, those have very small probabilities, but that's why there's no upper limit, although my plots all stopped at 50, just to keep them all on the same scale for comparison. I did a lambda of 5, which is where the mean is, which makes sense. If the most common thing to occur is 5, you expect most of your data grouped near that. I changed lambda to 15, and look at that, it's right in the middle. I changed it to 25, it's there. I changed it to 35, it's there. This thing, depending on lambda, of course, you get different shapes as well. You can see it's maybe more skewed for lambda for smaller values. And it becomes more bell curved as you get larger values of lambda. Here's a little example. We're crushing ore, and it's going into a processing plant on a conveyor belt. We're worried about pieces being too big. So the number of pieces found to be too large happens randomly, and during a 5-minute period that we have observed, because we watch this thing constantly, that 3.4 pieces are too large per 5 minutes. What's the probability that during a 5-minute period that they will find more than 3 pieces? So this is our example. I think we can see that it meets that Poisson feeling. Let's define a variable. X is number of pieces that are too large. During a period, a 5-minute period. So we have an interval. Rather than looking at a fixed number of pieces, we're going to look at basically time with our interval here. The average, I guess, the mean is lambda, which is 3.4 pieces per 5-minute. So it has the binomial feeling in that a piece is either too large or it isn't, but it doesn't have a fixed number of trials. It has a fixed time period. During that 5-minute period, let's assume that the pieces are equally likely to be, too large or okay. So we meet that uniform condition. The period is short enough that that's probably okay to assume. It might be better if this question said something like, you may assume that this is following a Poisson process, because it doesn't necessarily have to. Not all arrivals occur by a Poisson process, but it is very common. The probability that any individual thing is true here, it was lambda to the little x e to the minus lambda over little x factorial. And our question is asking, what are the chances that we see 3? Or actually more than 3? So this is the problem we're trying to solve. That means that it's 4 or more, because it's discrete. So we could calculate x equals 4, then calculate this for x equals 5, and then calculate it for x equals 6, and keep going. Basically, we'd have an infinite sum of terms that look like this. You'd probably be okay with that, as it kind of really has that sort of Taylor's series look to it. You probably would be able to manage this infinite sum. But why do so much work when we can just do the complement? We can say it's 1 minus the probability that x is less than or equal to 3. And then we just have to solve probability that x equals 3, x equals 2, x equals 1, and x equals 0. Don't forget about 0. And now we just have to substitute our values into this formula, 4 times. It's not too bad. So x is 3, our lambda is 3.4, and it's raised to the third power, then e to the negative 3.4 over 3 factorial. And then we do that for all of these. 3.4 squared, e to the minus 3.4 over 2 factorial, plus 3.4 to the first, e to the minus 3.4 over 1 factorial, plus 3.4 to the 0, e to the minus 3.4 over 0 factorial. Remember, 0 factorial is just 1. You'll notice that each term has e to the negative 3.4, so to speed up the calculation, you could just factor that out and then just add up the rest. It'll be quite a bit faster, I suppose, if you're using your calculator. I'm a little lazy. I probably just plugged this into Excel and got 0.4416. To do this in Excel, it's 1 minus Poisson.dist. We want 3 or less. So it's 3 or less, where the mean is 3.4. And yes, we want it to be cumulative. It goes x lambda cumulative. And 1 means yes and 0 means no. In fact, you can even write in there, I think, true or false, if you want. I think I did this in Excel too, so we can look at it. Here's the same question. I put lambda here, 3.4, and then I did Poisson dist for each one. I did probability of getting 0, probability of getting 1, 2, 3, 4. Again, the syntax is x, lambda, and then cumulative or not cumulative. In my table here, I said 0. I didn't want it to be cumulative because I wanted to build this chart. I wanted to know the probability of each event. It's rather nice to be able to see what we just did. This is what the distribution looks like, and we want the probability of more than 3. So we want 4, 5, 6, 7, 8, and continuing on. To solve it, we know that all the bars add up to 100%, and we took away 3, 2, 1, and 0. Here, if I can write on this. Maybe not. Anyway, to get my final calculation, that's just here. I did 1 minus Poisson dist of 3 or less. I did my 3.4. I just referenced the cell there. It's in cell B2. I don't really need the dollar signs here because I'm not copying it anywhere. And then 1 for cumulative. So we get our answer there. There's a 44% chance that we'll experience more than 3 pieces that are too large during a 5-minute period on this conveyor belt. Another example here, it's another binomial question, I assume. In an interactive time-sharing environment, it's found out that on average, a job arrives for CPU service every 6 seconds. So our mean is 1 job per 6 seconds. Assuming that arrivals satisfy Poisson, what is the probability that there will be 3 or less arrivals during a given minute? So our variable is arrivals during a minute. You'll see that our rate here isn't in minutes, so we need to adjust that. Don't adjust the question. Don't say, well, 3 or less in a given minute, and then multiply that by 60 so that we're into seconds. It doesn't work. You have to adjust the rate. So that 1 job per 6 seconds is equivalent to 10 jobs in 1 minute. So adjust the rate, not the question, because the question's asking what's the probability of 3 or less. I guess it's not poison. Poisson.dist 3, it's 10 jobs per minute, and yes, we want it to be cumulative. I have an Excel sheet set up for that already. I did the whole distribution just so we could see what it looks like. I said my rate over here was 10 jobs per minute. Then I calculated each probability using 10 so I can make the plot. Our goal is to find 3 or less so I can see that the answer is going to be a small number. It's just these rectangles summed together. Using Excel, I don't have to do 1 minus because it's already in the form of being less than or equal to. So, oh, I have a typo on my sheet here. It should say 3 lambda then 1. These two should be swapped around. And then we get our answer. And we're right. Looking at the picture, we knew it was going to be small, and it is. So roughly 1%. There's a cumulative Poisson table that works just like the binomial table. It's a table with a bunch of lambdas in it. So you pick your lambda, and then you go and look up your values based off of x. But Excel is pretty slick. I recommend it. Going back to the lecture again, you can see what's going on, maybe making you dizzy. Another distribution is a hypergeometric. Each one of these starts out with the line. Here's another distribution that's like the binomial distribution. It's sort of like the binomial distribution in that you have the two outcomes. Things are good or bad, live or die. But in this case, things are dependent of one another. When I start drawing cards out of a deck, you might think that trying to predict the color of the card would be a binomial situation. I take the first card out of the deck, it's either red or it's black. But then when I pick the second card out of the deck, it depends on what happened on the first card. And that's when we need to use the hypergeometric distribution, when we have dependence and a fixed number of trials. So I'm going to pick 5 cards from the deck, and so there's my fixed number of trials, and I'm going to ask the question, what are the chances that I get, 2 red cards in the 5 picks? So it's different that way. The formula involves combinations. It's A choose X, N minus A choose N minus X, over N choose N, capital N choose little n, where capital N is the number of cards in the whole deck, 52. A is the number of, say, red cards. Then X is how many cards you're going to pick that are red out of your subset of, say, size 5. So it looks kind of scary in the formula at first. Remember that A choose X is the same as ACX if you're using your calculator, which we know is A factorial over A minus X factorial, X factorial. So sometimes we kind of forget about that notation. Again, it's discrete, so our choices for X will be 0 and integers to n. The mean of this thing is, again, pretty easy to calculate. Standard deviation isn't quite as nice. We'll do an example. We have 18 new buildings, and we know that 6 of them violate city building code. Now we're going to randomly pick 4 buildings to go to. What's the probability that at least one of those 4 is in violation of a building code? So the big group is N, big N, which is 18 buildings. And 6 of those are bad. That's what the A was. Our building inspector is going to visit 4 of them. That's little n. And then X is the number in violation of the code. So that will help us with our variables if you're, strict about, using the formula. For me, these kind of make sense, where I don't really look at that formula that much. But again, I probably have a little bit more experience than most on this. We want the probability of at least 1, it says. So x greater than or equal to 1, which means 1 or 2 or 3 or all 4, because we're going to 4 buildings, which is a lot of work. So maybe we should find the complement. The opposite of greater than or equal to 1 is none. So this won't be too bad to calculate then. There are 4 buildings out there. I'm looking at 4 buildings, and I don't want any of them to violate the building code. So I know that 6 of them violate the building code. I don't want any of them. I want 0 out of 6. Then there must be 12 that don't violate the building code. You know, there are 18 in total. 6 are bad, means 12 are good. Of the bad ones, I don't want any. Of the good buildings, I need 4 of those. And I'm going to divide that by all the different ways that I can pick 4 buildings out of 18. So there are 18 buildings, and I'm choosing 4. So basically, all the different ways that I can pick a building that is in violation, but I don't want any, times the number of ways I can pick ones that aren't in violation, and then divide that by the total number of ways I can choose 4 buildings. You can plug these combinations into your calculator. You'll get 0.8382. Or you could use a function in Excel. It's hypergeom.dist. And then the parameters are really tricky. I think it goes x first. Then I think it goes little n. Then it goes a, then big N, and then cumulative. I'm not sure. I'm going to just say I'm not sure about the order of these parameters. The nice thing about Excel is that once you start typing the formula, it will prompt you with those things. Let's go give it a shot here. So in Excel, in our example, we had 4 in our sample. There were 6 successful buildings that were in violation of the code out of a total of 18. Hypergeom.dist is the first value is x, then the second value is little n, then the next value is a, and then capital N, and then cumulative or not. So it goes x, n, a, big N. I think I had it wrong. X, N, A, big N. Oh, good for me. When you're actually typing these things, like you'll see, I can get it to, if I click into the formula, below it, it starts to prompt you, although they're pretty cryptic. Sample S is like my sample size of 4. The number, oh no, it's sample successes, then number in the sample, then population successes, number in the population, and then that cumulative flag. Whew. Oh no, now I'm changing my formula. I don't know how to get out of this. I don't know what it is. An escape key. Oh, I have to leave tablet mode. Okay. So I calculated the probabilities of no buildings, one building, two buildings, three buildings, or all four buildings having a violation of the code. And the graph is here. It's pretty skewed to the right. We wanted the probability of greater than or equal to 1, which is 1 minus the probability of less than or equal to 0 or equal to 0. Plugged in the numbers here, it's 0 out of 4, where 6 out of 18 are bad, and I said not cumulative. And we got the answer of 83, 82. So that's pretty fun, I guess. Calculating the mean and standard deviation of that thing, it's basically just, plug it into the formula. The mean for a hypergeometric is little n times a over big N. So in this case, we're looking at 4 buildings where 6 out of 18 are violating the code. So you get 1.3 buildings if it's repeating. The standard deviation is a little bit of a beast. It's little n(a) times capital N minus a quantity. Capital N minus little n, I'll remember it, all over n squared n minus 1, and then we need to square root all that. Plugging in those numbers, little n is 4, a is 6, big N is 18. We'll end up with 0.855 buildings. The units are the same. So we can see it on the graph here. The mean 1.3 seems reasonable. And the standard deviation is pretty small here. It's under 1, which means we expect stuff to be pretty close to that. And it is. So that is pretty consistent with what we've seen before. Whew. Each one of these is not so bad. The way it gets to be problems is that when you get to, say, a midterm, you have to figure out which question you're dealing with. You'll read the question and you go, is this one of those Poisson ones? Or is this one of those hypergeometric ones? But once you figure out which one it is, and once you figure out your greater than or equal to or less than or equal to, then it's straightforward from that point. But the hardest part is definitely just recognizing, which distribution you're working with. The next distribution is pretty straightforward. It's got the geometric distribution. I'll start out. It's like the binomial distribution where you have only 2 outcomes, but you're waiting for the first success. So that's the difference with this type of problem. So these stand out. The problem itself has to be worded in such a way that you don't care about a number of successes. You're trying to figure out sort of when you're going to get your first success. So are you going to have to try 10 times before you succeed or 4 times before you succeed? Those will be the probabilities that we'll be calculating. So basically, the formula for this makes a lot of sense to me. You can't succeed before you've even tried. So you can see that our variable starts at 1 instead of at 0. If you look at this thing, it's like you need to fail a bunch of times and then finally succeed. I almost wish it were written that these two terms were swapped around, that it were 1 minus p raised to a whole bunch of failures, and then you succeed. 1 minus p is the probability of failure, and you fail a whole bunch of times, and then finally you succeed. Your mean is just the rate, 1 over p, and your variance is 1 minus p over p squared. We have a photocopier that's shared at BCIT, and it seems like the thing is always busy. And it's too far from my office. I can't tell if there's someone there or not. So I get all my stuff ready. I walk to the photocopier and there's someone there. So I go back to my office and do something. Then I come back a little while later and there's somebody there. And I do this until finally I get to the photocopier and yay, it's open. I get to photocopy. What's the probability that it will take me 5 or more trips to the photocopier before I finally get my copying done, if that thing is busy 75% of the time, which it does seem like it is? I'm not bitter or anything. Let's let our variable be number of attempts. So I want the probability of needing 5 or more attempts. Again, there's no upper limit to this, so this would be an infinite sum if we try to do it directly. Find the probability of 6 tries, 7 tries, 8 tries, 9 tries, and then, sum that infinitely. Or do the complement. The opposite of 5 or more is 4 or less. Again, because it's discrete. I mean, this isn't true of all math. In the continuous case, we wouldn't write this. But it's very important to get this number right, because this is the number that you plug into formulas in Excel. So if you put in 5 into your Excel formula here, you get this problem wrong. So, it's 1 minus the probability that we have exactly 4 tries, or it takes me 3 tries, or it takes 2 tries, or it takes 1 try. I guess it can't take no tries. So I need to do that formula, this 4 times. So there's a 75% chance that I'm successful. So, or no, there's a 75% chance it's busy. So 0.75, I need it to be busy 3 times and then finally not be busy. And the nice thing about this distribution is you don't have to worry about permutations and combinations, because there's just one ordering of that. Fail, 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 and then succeed. Now I need to fail twice and then succeed. And then I have to fail once and then succeed. And then I just need to succeed. Doing a little calculation there, you get 0.3160. About 31% of the time, it takes me 5 tries or more. So I get my exercise trying to get my photocopying done at BCIT. Actually, they've improved the photocopiers quite a bit now. I can just email the document to the photocopier, and it will just print when whoever is there is done. So it's really not as bad as I make it out to be. But back in the old days, used to have to do that. On average, how many attempts does it take me to gain access? Let's figure that out. The probability of success here is, be careful, it was 0.25. There's a 75% chance it's busy. So there's a 25% chance it's open. So well, the average number of attempts is just 1 over p, so 4 tries. On average, I get my prints in 4 tries. So I budget my time accordingly. If you're interested in this in Excel, I don't think there's a function for the geometric distribution, but you can just make your own. You know, it's p times 1 minus p raised to the x minus 1. So I just made my own custom formula there. It's the probability, which I have in B2, times the probability of failing, which is 1 minus B2. And then I raise it to whatever x is, but I have to subtract 1. And then just copy that formula, down. You can see the plot here. It's very skewed. And then to build the answer here, I just added together because it doesn't have a cumulative formula. I just built this table and added these values together. I wanted 1 minus 4 or less, so I just calculated the probability of 4, 3, 2, and 1 and added them up. So sadly, that function isn't in Excel, but it's easy enough to make our own. In fact, I could probably share this document with you, and then basically you have a template for making any of these. All you have to do is, for your whatever question you're working on, change the probability of success, and it will even graph the thing for you. I mean, you just have to do some modifications to, this, depending on your problem. So that's good. The last distribution. Wow. Who knew this was going to take so long, right? Is the multinomial distribution. It's like the binomial distribution, except it has more than 2 outcomes. So now instead of having 2 outcomes, this is like you get an A in the course, you get a B in the course, you get a C in the course. Each one of those things has some possibility of occurring. The formula looks just like the binomial, except now I have the Mississippi rule at the beginning of it for each category. Here's a little example. I think it'll make some sense. It makes more sense almost with the example than with the formula. The probability that a person will pass this stats class is 95%. The probability that they withdraw before it's over is 1%. And the probability that they will fail is 4%. I think it's probably lower than that, actually. It's close to that. It seems like around 1 student fails per year in the last few years. So I guess that's around 30, or around 3%. So this isn't that far off, although almost no one ever withdraws. But I needed 3 categories to make it into a binomial situation or multinomial situation. I have a small class of 14 students. What's the probability that 11 pass, 1 withdraws, and 2 fails? So I have x1, which is my pass. Variable 2 will be my w's. And variable 3 will be my f's. What's the probability of getting this certain permutation? I have 14 students. I need it to be exactly like this, where I have 11 passers, 1 withdrawer, and 2 fail. This probability will be low. In fact, with these multinomials, each one will always be low because there are so many different permutations. Each individual one has to have a fairly low chance of happening, so that when they all add up, you end up with 100%. It works like this. You have 14 factorial. If they were all unique, there'd be 14 factorial ways, but I can't tell the 11 people that pass apart. You're all just numbers to me. You're just people that pass, or you're people that don't pass, or you're people that get W's. So if I have two people that are passing, I can swap them around and it's the same thing. Same with the withdrawers and the fails. Now we take these probabilities of happening. There's a 95% chance that you pass. I need 11 of those. There is a 1% chance that you withdraw. I need one of those. And then there's a 4% chance that you fail, and I need two of those. Grind all that out. It's low. It's 0.009938. These will all be fairly low just because there have to be so many different ways everything can happen. So to ask for any one particular order is, will always be low. Excel doesn't have this multinomial function either. It does have a function called multinomial, which will figure out that the number of permutations. So multinomial is your Mississippi rule, where you just input the number of unique items in each subgroup. So you had 11 passers, 1 withdrawer, and 2 failures. But then I had to complete the formula myself by doing the powers. You'll see we get this same result. But again, now you can use this formula if you'd like, or this template. I'll try to remember to post this for you guys. I think that's it for probability distributions. We've done a whole bunch of discrete ones. Believe it or not, there are others. But I think this is a pretty good coverage of this. The next time I see you, we will move on into continuous probability distributions, which will have a whole bunch of those to cover as well. So I hope you guys have a great day, and I hope you look forward to continuous probability distributions next. I'll see you all next time.